Hey guys, welcome back to another Leetcode video. Today we're going to be looking at Leetcode 153, find minimum in a rotated sorted array. In this problem, we're told that we should suppose we have an array of length n sorted in ascending order, and this ascending order list has been rotated between 1 and n times. So for example, list nums 0, 1, 2, 4, 5, 6, 7 will become this list if it's rotated 4 times, and this list if it's rotated 7 times. So we can see that there are pivot points, right? In this case here, the pivot point is here. In this case, the pivot point is here, but because we pivot 7 times, we rotate seven times, sorry, we just end up exactly where we were initially, right? And so you can see that if it's rotated 4 times, it will have 4 elements that are wrapped from the end round to the beginning. So that's basically what rotation is. We rotate a list around a pivot point. So we're given this rotated sorted list, and given this list, we are told that of unique elements, we're told that we want to return the minimum element of this list, right? And we want to write an algorithm that runs in big O of log n time. So, this is kind of the part that catches people out, because this means that we want something that's not linear, right? I mean, the linear solution is just to go through the entire list in big O of n time and, look at each element and then return the smallest one. We want to write an algorithm that runs in big O of log n time. What does that mean? Well, just looking at this problem, what algorithm will give us big O of log n? It will be binary search. So we want to somehow employ the binary search technique to solve this problem. Okay, so how would we solve this problem? Well, let's take this example over here, 3, 4, 5, 1, 2. So we'll say 3, 4, 5, 1, 2. Okay, so we have this list over here, and what we can say is our midpoint is going to be over here, right? So that's our midpoint, 5. We want to check, we know that there's 2 sections here, right? There's a left section and then there's the right section. So the right section is, has values which are smaller than the left section. So if we're in the left section, we want to check in the right section. If we're in the right section, we want to check in the left section. So how do we know which section we're in? Well, we know that we're in the left section, if the mid value is less than or equal to the left value. So in this case, is 5 greater than, so if the mid value is greater than the left value, or the value at the left pointer, so if 5 is greater than 3, that is true. So what we can do is now look at the right portion of the list. Okay, so we can just scribble out 3, 4, and 5 because we know that these are all in the left section, and now we want to look in the right section. We're left with these 2 values, 1 and 2. 1 is at the left pointer, 2 is at the right pointer. What can we look at? What can we check here? Well, we can say the left value is less than the right value. Therefore, this list is now sorted. So we can just return the left value, because this could be the minimum value in the list, and that does tend to be the case. Here we can, it tracks that 1 is the smallest value. So let's get to coding this up. That's how we're going to solve this problem using the binary search technique. So the first thing we want to do is have a result. So, initially we want to have our result set to infinity because we want to be able to overwrite it as we go through our list. And then we want 2 pointers. We want a left pointer and a right pointer. Left pointer is equal to 0. Right pointer is equal to the length of nums minus 1. And while the left pointer is less than or equal to the right pointer, if the number at the left pointer is less than the number at the right pointer, well, then we can just say result is going to be equal to the minimum of the result and the number at the left pointer, and then break out. Right, this is the condition where the list is sorted. Otherwise, we want to do binary search, so we want to say left plus right divided by 2, result is going to be equal to the minimum of the results and the number at the midpoint, nums mid. And what we can do next is say if nums mid is less than or is greater than or equal to nums right, or sorry, is greater than or equal to nums at pointer L. In that case, we can check in the right hand section, so we can say left is equal to mid plus 1, else right is equal to mid minus 1. Right is equal to mid minus 1. And then once we're finished from our while loop, we can simply return our result. And we can see that our solution is accepted and passes all 150 test cases. And we have quite an optimal solution, again, because we are employing binary search and it runs in big O of log n time. So that is the solution for this problem. If you've solved other binary search problems, you might have figured out that intuition is fairly simple, especially when it comes to detecting, the key part is really detecting which section we're in, whether we're in the left-hand section or the right-hand section, and then running binary search and finding the minimum value based on those criteria. So in terms of time complexity for this problem, we're looking at a big O of log n. So big O of log n time. And for space complexity, we're looking at big O of 1 because we're only using auxiliary space. So with that being said, guys, I hope you found this helpful and I'll catch you in the next one.